Hey everyone, welcome back to another video in our predictive analytics series. I wanted to take some time to go through a notebook with you all discussing model building frameworks. So this is a framework for the way we take data, construct a model, and then objectively assess the performance of that model. What I've been advocating for so far in our course is that we start our analysis by taking a peek at the overall structure of our data set, kind of identifying where we might have missing data and other issues that we're going to have to kind of uh, remedy before we move forward into building a model. But beyond that, before we start any exploratory data analysis or data visualization, I've been advocating that you all split your data into a training set and then one or more validation sets. We do that because the validation data is hid away from our model during its training process. And it's actually hidden away from us too during our exploratory phases where we're kind of gathering information and insight as to what types of model might perform best and what types of features we might use or engineer. So it's important to have those holdout sets as unbiased tests for our model's performance. There are other model building frameworks, and in fact, the model building framework that we've been using has some significant shortcomings. I wanted to take this video to kind of highlight those and to introduce really briefly, without using it, an advanced model building framework that we're going to start using for the remainder of our course. All right. So with that, let's just get going. We're going to play with some toy data here. You're used to that at this point. Toy data is pretend data that we're randomly generating with the use of the computer. So this data doesn't mean anything. It's randomly generated once we run this cell. We're going to import NumPy. NumPy is giving us mathematical functionality and that ability to generate random numbers. Pandas is our functionality to manipulate data frames. We've been using pandas a lot in our course. Matplotlib and Seaborn, you've seen quite a bit again. These are plotting libraries that allow us to draw pictures. And then from the scikit-learn model selection submodule, we're going to import train test split, which we've been using up to this point to split our data into training, test, and safe sets. Now that we've imported all of our libraries, we're going to generate our data. So I'm going to generate two predictor features, X1 and X2, and one response. That response will be related to our predictors. Both of the predictors come from uniform distributions. I've been doing this for the most part when we've generated toy data. They both pull random observations from the range 0 to 100, and we're going to have 50 observations of each. We want an X1 coordinate and an X2 coordinate for each of our records in our data set. Once we have those, we're going to create a response Y. That response is related to the two input features that we just generated. So this is the function that we're trying to recapture through modeling. It's a little bit more of a complex function. It's not sort of a plane. It's going to have some curvature associated with it because of this x1 times x2 minus 50 term in here. So it's a more complex relationship between the predictors and response. Like usual, we're going to add some noise in here. The noise forces us, the noise brings us away from a deterministic problem and into this data modeling problem. It makes the tools like regression necessary. So remember, the noise just is used to bump our observations, our response variable, kind of above or below the deterministic function that we're using to kind of generate this relationship. Once we have that done, we're going to create a data frame. The data frame has 3 columns, the 3 columns corresponding to the 3 variables we just generated, x1, x2, and y. Then we're going to use train test split. For now, I'm just going to split into training and test sets. So what we've been doing in our class and in our analyses, we've used train test split twice to get a training test and a safe set. We don't need the extra safe set here. This is just to drive conversation. So if you remember, train test split takes in some data. It takes the size of the training set we want back, and we use a random state for reproducibility. Once we've done that, we're going to create some plots just to see what our data looks like. So let's run this giant code block. It's all just generating data, splitting the data, and plotting it. So here we've got two plots, the response that we're trying to predict against the x1 variable, and the response that we're trying to predict against the x2 variable. We can see a three-dimensional scatter plot, but you see why I've advocated against using three-dimensional plots, or at least where all three dimensions are attempting to be spatial dimensions, because this isn't really that readable. We can't see any real relationship here. What I'll do is I'll create another plot where we are trying to visualize all three of our variables here. We've got x1 is going to be along the x-axis, x2 is going to be along the vertical axis, and let's define the color according to the y, according to the response variable. So we'll get different shades here. Okay, and this plot is potentially a little bit more readable than the three-dimensional scatter plot we tried to build. We can see that points kind of in this upper right corner seem to have smaller response values on this scale. Points in the lower right corner seem to have the highest response values. And so there's some relationship here. There's definitely a relationship between x2 and our response. As we move vertically through this space, the response values change. As we move horizontally, it's less obvious what's happening. We don't see much color change horizontally through our plot. There's the data that we're going to try to model. We have a really small data set. We've generated 50 points. 37 of those have gone into the training set, and 13 have gone into the test set. Let's build our models. So we're going to build a straight line linear regression model that uses both of the available predictors x1 and x2. So this straight line relationship is going to assume that there's no curvature between no curvature in the surface we're trying to model. We know that that's not going to be a good assumption, so this model is probably going to perform poorly. So what we're going to do is we're going to import the linear regression constructor from scikit-learn's linear model. We're going to create an instance of that linear regression constructor, and then we're going to fit it to our training data. So when we fit it, we're allowing access to the predictor columns, both x1 and x2 here, and the response column y. This is the target variable for the linear regressor. Once we have that fitted model, we can use it to make predictions. So what we'll do is we'll jump straight to making predictions on the test data. So we're passing the test data frame along with the columns x1 and x2 because that's how the model was trained. So it got a data frame whose only columns were x1 and x2, and it was allowed to make predictions using that. So now when we use the prediction function or predict method, we have to pass a data frame that looks similar. Then let's create a plot. So we're going to create, again, two plots. We're going to plot the original data. This is the training data. Then we're going to plot the test data. So these are going to be new points coming from the test data frame. They're going to be in black. We're going to plot our model's predictions. They'll be in red. So we'll have three groups of points here, one blue group, one black group, and one red group. What we really want is we want to see the red points close to the black ones. That would mean our model's making strong predictions. And then we'll label the axes here. What we're showing in this plot is the relationship between the x1 predictor variable and the response or the predicted response. Then in the second plot, we'll do the same thing, but the horizontal axis is going to correspond to the x2 variable rather than the x1 variable. In addition to printing out those two plots, we're going to print out an error metric for our model. So we'll print out the test root mean squared error. All right. So we can see it's faded in the background here. The light blue points are the data points that the model knew about ahead of time. So the model knows where all those blue points live. The black data points are the observations in the test set. The model didn't know about those observations. And the red data points are the model's predictions for those unknown test observations. You can see that with X1, the model isn't doing so good a job. It's not getting really close to those black data points. And it would have a hard time doing so anyway, because it seems like most of the fluctuation here is noise. As with X2 though, the model's doing a much better job. At least it's capturing a real general trend in not only the training data, but also the test data. Okay, so now we might say, okay, the model seems to be doing kind of well in predicting the test observations. We can definitely make improvements though. Maybe we do better by adding some curvature with respect to X1. So we're having trouble here in this left panel. Maybe changing how our model deals with X1 will give us some benefit. I'm going to put a black star here and we'll come back to that black star later. But let's, for now, just see if that change improves our model performance. We'll explore model performance visually, but also using this test root mean squared error. So right now, we have a test RMSE of above 900. Without any context, we don't know if that's good or bad. All we can say is, well, now this is our new benchmark. We're going to try to beat that test RMSE. We're going to try to do better than it. So here, we'll build a new column in both our training and test data frames. We're going to call it X1 squared. We're going to get that column by looking at the X1 column and squaring it. We'll do that both for the training data and also for the test data. We'll create a new linear regressor object. I'm going to call this one curvy linear regression because this one now is going to allow for some curvature. That's in here with the squared term. And when we fit the model now, we're going to allow that model to have access to X1, X2, and X1 squared as 3 predictors that it has access to. So it has access to all of this information as it tries to predict the Y values. Same deal, once that model is fit, we're gonna use the predict method to make predictions on the test data. So we're passing those same columns from the test data set to the model and its predict method. Then we're gonna draw plots. These are gonna be the same plots as you saw earlier with blue dots in the background. Those are the original training data that the model knows about. Black dots are the test data points, and then we'll see in red how closely our model's predictions come to those test data points. And we're going to do this again. We'll plot once for X1 versus Y and once for X2 versus Y. We'll also print out the test RMSE. If you remember, our last test RMSE was a little above 900. I think it was 919. So let's see how this new model does having access to the X1 squared term. And so we can see in terms of the test RMSE, we're doing a little bit better. We've dropped down to near 850. So this is an improvement. We can see that the red data points here are getting a little bit closer to the black target data points. And so this has been a slight improvement. So it was a slight improvement, but it didn't give us a whole lot. Maybe we can do even better. Maybe we can do even better by looking at the product between X1 and X2. So let's build in another new column. So what we're going to do is we don't actually need to build the X1 squared column already. It's there. It's just here for completeness as I was constructing the notebook. Then we're going to build an x1 times x2 column. That new column is going to have name x1, x2. We're going to get it by taking the x1 column and multiplying it by the x2 column. Because we ultimately want to not only train our model, but also make predictions with it, we're going to do the exact same thing with the test data. So we're going to give the test data this new feature as well. We're going to define another new linear regression constructor. We're going to fit that linear regressor on the training data, now having access to 4 columns of predictors, x1, x2, x1 squared, and x1 times x2. And we're still trying to predict the response variable, which is y. Once we have that model fit, we're going to make predictions, again, passing the same columns so the same columns from the test data as the model was fit on with the training data. So x1, x2, x1 squared, and x1 times x2. And then we'll again create those plots and grab a computed test root mean squared error. So 857 was our benchmark to beat now, and we're way down to 521. It looks like we made some real breakthrough here by adding in that interaction term between x1 and x2. This was really valuable. Okay, so we made real improvements here, but there's a kind of a big problem with the way we approached this analysis and model construction. Remember that the test data was supposed to provide an unbiased assessment of our model performance. Our model wasn't supposed to know anything about that test data. Except now, the way we performed our analysis, the model does know quite a bit about the test data, actually. In both of these sections where I added a black star, we had looked at our model's performance on the test data. And we said, oh, we're missing the test data points. Maybe we can do better by adding in some curvature. Or we're still missing the test data points, but maybe we can do better by adding in some interaction between our two variables. We got information about the test data set, and then we used that information to inform decisions that we made about our model construction. Now we're leaking information from the test data set into the training process. We are part of the training process. And so because we learned about the test data, the model learned about the test data. This is bad. And so we are in danger of overfitting because of the choices we made with knowledge that we shouldn't have had. So we allowed the validation data to become part of our training data. This is sometimes called leakage. We're going to address this later on, so I'm not going to talk about it yet. Simply put, so another problem, we validated our model on a single set of test observations. How do we know that that wasn't just an easy set of observations? Or how do we know that it didn't, by chance, contain the most difficult observations to predict? How do we know that the test data is actually representative of the population that we want to extend this model's predictions to? It's tough to make those claims when we've dealt with just a single random data set. We're kind of leaning on randomness quite a bit. We're putting a lot of trust in it. So let's talk about leakage for a little bit. We've talked about those black starred sections in the notebook where we looked at the model's performance on the test data, and we used our insight into that performance to make model construction decisions. We added in a squared term, we added in an interaction term. We've told the model something about the hidden data that it shouldn't know. I mentioned this, but I do want to highlight it. As analysts and data scientists, we're extensions of our models. So that means that we shouldn't have access to insider information about the data that we're going to use to assess those models. That being said, there's certainly actually quite a bit of value in seeing the types of observations that our models perform well or poorly on. And so actually looking at the test data is something we want to do, because we want to have an idea of whether our model is performing well or poorly. And in particular, where is our model performing poorly? Can we make tweaks to our model that might improve its performance in those areas? So here's where we're at. We can't know anything about our hidden validation data because we're going to end up leaking that information to the model. But we need to know about how our model performs on hidden validation data. We need to know that so that we can make adjustments and improve our overall model performance. So how do we fix this? We can't look at the validation data, but we have to look at the validation data. And so this is actually why I've been advocating so far in our course for the train, test, and safe set approach. So this is where we've been taking our data set, breaking it up into a training and temporary set with train test split, and then taking that temporary data set and splitting it in two pieces. One is a test set and one is a safe set. The test and safe set are both validation sets that we'll use to analyze our model performance. But because we have two of those sets, we can set the safe aside and not touch it until the last minute, or like the last part of our analysis, just one final assessment of the model that we hope to move forward. This allows us to train our model on the training data, see how well it performs on the test data, make adjustments to our model and retrain it, perhaps look at models of competing classes, retrain those, kind of have them battle it out on the test data, and have this iterative process of training and assessment, then going back and making edits to our models, retraining and assessing. And this allows us to really improve our model performance. And then having the safe set still off to the side allows us to continue to have access to an unbiased assessment of our model performance. So that's an improvement over the training and test set approach with a single validation set. So we've been using training, test, and safe, and that's why. But again, not so fast, because even if we do train on one data set, we have a test set to kind of intermediately to give our model some intermediate tests that then inform how we adjust our models, and then we have the safe set off to the side. We're still really leaning on randomness. So we still have these questions about, well, how do we know that we have the right training data? We used randomness to get it. Are we willing to trust randomness? How do we know that we have a fair test set? Our test set that's kind of guiding our model, our modeling decisions along the way, how do we know that that's guiding our decisions in the right way? And are we sure that we have an unbiased safe set that's representative of the overall population of observations that we want to extend our model's predictions to? We don't. And to make it all worse, the more flexible the model we decide on, the more that model is going to change given some different training data. Remember, we talked about bias and variance. Very flexible models have high variance, which means that they're going to change if they're going to change more if they're given different training data than a less flexible model would. So we're really at the mercy of randomness here, and this means that if we choose a flexible model, we could have really different performance assessments, model predictions, if we just switched our random seed. We don't want that to happen. So having a single test set or even two sets of observations to test our models allows random chance too large an influence in our decision-making process. So this brings us to a method that we're going to be exposed to very shortly, and it's a method that we're going to use moving forward. It's really powerful. So cross-validation. in the typical validation set approaches that we have been using, we started by shuffling our data set and breaking it into either 2 pieces or 3 pieces randomly. Our models learned or were trained on the training data, and then we assessed them on the validation sets. Validation sets might be too difficult or too easy or not representative of the population that we want to make predictions on. So that's an issue. And it's leaning too heavily on random chance and our choice of seed. So there's also another concern. And the other concern is that in doing this and hiding the test data and the safe data from the model, our model never gets the benefit of learning from those observations. Their information is totally kept away from the model. In the case of the safe set, it's really kept away. It's never leaked to the model. So in cross-validation, so I guess I should point out that, what if perhaps some of the observations that fell into the safe set were particularly important? And our model never gets that information. So an alternative to the validation set approaches that we've introduced is called cross-validation. I'll try to explain cross-validation briefly here, and then we'll end up using it starting in our next notebook. So in cross-validation, all observations get an opportunity to be in training sets, but they'll also have opportunities to be in the validation set. Observations can't be used for both training and testing simultaneously. So, and the reason for that is because the model would have an advantage in predicting that observation's response, because the model would have learned it through the training process. So here's how cross-validation works. We're going to start by shuffling the observations in our data set, just like in the validation set approaches. So we take all of the rows in the data set and we shuffle them around. Then, rather than splitting the data set into piles, we're going to mark each observation as belonging to a fold. We're going to do this in such a way that the folds are approximately the same size. Sometimes it's not possible to have all of the folds exactly the same size, but they're going to be close to the same size. Most often people will choose 5 or 10 folds, but you can have any number of folds. We could even go so far as to put each individual observation into its own fold. So as kind of a mental paradigm here, we can think of this as if our data set's rows were a deck of cards. So each row was a card in this deck. We shuffle the deck of cards. And then on each card, let's say we draw a symbol. So a square, a triangle, a diamond, a star, or a dagger. And then the symbol drawn on the card corresponds to the fold that it belongs to. So the folds are just like groups that the observations belong to. So now we have a shuffled data set where each record belongs to a group. So now that we have the observations assigned to a fold or to a group, we're ready to start modeling. We can assume, let's say that we use 10 folds. So what we'll do first is we'll set the 10th fold aside, and we're going to train our model using the observations in the first 9 folds. So we're taking folds 1 through 9. They're the entire training data set for the model right now. We're going to train the model on that data. Then we're going to assess it using the observations that belong to that held out 10th fold. So now we have a model built. We have a corresponding error metric for that model. So something like the root mean squared error. Then we'll set the 9th fold aside, and we'll train our model on folds 1 through 8 and also 10. So we're training our model on 9 folds again. We're holding out a different fold's worth of data. Again, we get a trained model, and we use it to assess the observations coming from the 9th fold. Again, the 9th, the observations in that 9th fold were not shown to this model. This model was only trained on folds 1 through 8 and 10. So the observations in the 9th fold are an unbiased assessment. We'll get another error metric from these, so another root mean squared error. And we're going to continue doing this process. So each fold is going to take one turn being left out of the training process. And it's going to come back as the validation set for the trained model. Once this is done, if we've used 10 folds, we're going to have 10 estimates of model performance, one estimate for each of the models we built. We can then aggregate or average these estimates to obtain a cross-validation error estimate. There are a lot of advantages to the cross-validation error estimate. This is much more stable than errors estimated using the typical validation set approach. So if we choose different training sets, test sets, and safe sets using the validation set approach, we could say 20 of us build models on different training data, assess those models on different test data. We may get a very wide range of error metrics. If we all used cross-validation, we'll still get slightly different error metrics, but they're much more likely to be close to one another. Much more stable. And this is due to the averaging that happens to obtain that cross-validation error estimate. What we're going to use moving forward, so that's a short discussion on cross-validation. You'll see it in action in our next notebook. Cross-validation has actually many more advantages than just giving us a stable error estimate. It actually helps for model selection. It's going to help us determine what's the appropriate level of flexibility for our models. So you'll see that in the next notebook. What I'm going to advocate that we switch to now is kind of a hybrid approach. We started our course with the validation set approach using both a test and safe set. We're going to use cross-validation now. We still will need a safe set, is what I'm going to ask. So we're still going to split our data. We're still going to have this held out safe set for kind of a last sanity check on our model's performance. But we're going to start using cross-validation rather than just a single training and test set. All right, I hope this has been useful and enlightening. Thanks for sticking with me, and I'll see you next time. Take care, everybody.